I welcome all of you to the class, and today we are going to discuss problem 20.2. As far as the problem 20.2 is concerned, the problem 20.2 states that the disk rotates about z-axis at a constant rate of omega z equal to zero point 0.5 radian per second without slipping on the horizontal plane. Determine the velocity and acceleration of point A on the disk. So the question states that we are having a disk we have a disk which we represent by D, and this disk is rotating on a horizontal plane, okay, with an angular velocity of 0.5 radian per second. If we look at the disk is rotating about z-axis, omega subscript z equal to 0.5 radian per second. As far as the rotation of the disk with respect to z-axis is concerned, the rotation of the disk about z-axis is possible because of the bar, that is B, to which the disk is attached. The disk is attached with the bar, and this bar, it's the rotation of this bar, okay, about z-axis, which is equal to 0.5 radian per second, which is responsible for the rotation of this disk about z-axis. We mean to say that the rotation of the bar with an angular velocity of 0.5 radian per second causes the rotation of this disk as well about z-axis with a velocity, angular velocity of 0.5 radian per second. Okay, so as far as this data is concerned, apart from this data, we are also given that the disk is rotating without slipping on the horizontal plane. Now we need to understand this motion precisely. As far as this statement is concerned, that the disk is also rotating without slipping on the horizontal plane, it gives us a broader insight into the question, in the sense that it's actually the disk which is subtending some angle with respect to the base, with respect to the plane, with respect to the horizontal plane. Okay, and this disk is actually rotating, or I mean to say it is spinning. It is spinning in such a way that its spin is responsible for its overall rotation about z-axis. Okay, so if we look, it means that this disk should be spinning in this way, in a sense of clockwise rotation. As this disk is spinning in this direction, in the clockwise direction, okay, that is, at this point the spin is clockwise, and this wheel is then turning, this entire disk is rotating about the z-axis. So what we are given, that the disk is spinning about this central axis. Let me draw it precisely, about the central axis. Okay, so in such a way that its overall angular velocity about z-axis is equal to 0.5 radian per second. That is possible when this disk will be rotating in a sense of clockwise direction, because if this disk happens to rotate not in the clockwise direction but in the, say for example, the anti-clockwise direction, if the disk spins in the anti-clockwise direction, then its sense of rotation will not be along z-axis, positive z-axis, but it will be along minus z-axis. So it means the disk is somewhat rotating, spinning about in a sense of clockwise rotation, and its overall motion about z-axis has an angular velocity of 0.5 radian per second. So if we curl our fingers in this direction, okay, so the vector of its rotation, the rotational vector of this direction of this will be in this direction. The sense of rotation of this disk will be in this direction. Let's now represent it as a rigid body in two frames. Let's take our disk as a rigid body whose motion we are trying to understand, because we have to find the velocity and acceleration of point A of the disk. So disk is a rigid body for us. Disk is the rigid body for us. Okay, disk is the rigid body for us. Apart from disk being the rigid body, we are having two frames of reference. One frame of reference will be treating this bar. We'll be calling this as the bar frame of reference, and we are also having this frame of reference, okay, where our O and O prime, that is the center of our ground frame of reference and center of the bar frame of reference, are actually intersecting, okay. So we're having the ground frame of reference. Let me clean the diagrams to draw them more precisely, representing my frames of reference. First of all, I will say this is the ground x-axis, this is the y-axis of the ground frame of reference, and this is the z-axis of the ground frame of reference, okay. So I will first of all state that this is the origin O and this is my ground frame of reference, okay. So I will represent ground frame of reference with capital letters. This is capital X, capital Y, and capital Z, okay. And another frame of reference will be the bar frame of reference, okay. Let me suppose the origin of this bar frame of reference is also at the same point as the origin of the ground frame of reference, and this bar frame of reference is having x-axis represented by small x, y-axis represented by small y, and z-axis represented by small z. This is something important, okay. And so now we are having two frames of reference. The what is being represented by the capital letters is the ground frame of reference, and what's being represented by these small alphabets is the bar frame of reference, number one. Number two is the ground frame of reference we are assuming to be at rest, okay. But as the disk is rotating about z-axis, so our y-axis, our x-axis, the entire system keeps on rotating about the z-axis. So our small x, small y system is rotating. Bar frame of system is our rotating with respect to the ground frame of reference, capital X, capital Y, and capital Z. Now, let's now visualize or understand or initialize the data in terms of our two frames of reference. This is ground, this is the bar. I will represent bar frame of reference by B, okay. And this is our rigid body, the disk. I will write this as disk D. Now let's see what data we are given. It says that the disk rotates uh, at about the z-axis at a constant rate of 0.5 radian per second, okay. So the disk is rotating. I said earlier that the rotation of disk is possible when the bar will be rotating, okay. It's actually the rotation of the bar along z-axis which is causing the rotation of the disk about z-axis. Actually what's happening, the disk is spinning in this way, okay. The disk happens to be spinning and it's having the point of contact with the base, as a result of which the disk keeps on spinning about the z-axis. So this omega z that we are given, it's actually the angular velocity of the bar with respect to the ground, and it is equal, we are given this is equal 0.5 radian per second, and it's along k cap, okay, along k cap. This is one. And we're also, it's also stated that the disk is spinning, okay. Let's suppose that as the sense of rotation of the, as the sense of spinning of the disk has to be clockwise. If we curl our fingers in the direction of this, if we curl our fingers in the direction of this arrow, then the spin vector of this disk will be in this direction, okay. And we'll call this as, this is spinning vector omega s, okay, which also represents, okay, the, I will write here the angular velocity of the disk. This also represents the angular velocity of the disk with respect to the bar frame of reference, okay. That's equal omega s, and that is, hopefully we don't know, we have not been given the value of omega s, which we can certainly find out, okay. Now uh, let's, as we have initialized things in terms of frames of reference, let's try to now understand this question properly, what the question was trying to state. Okay, the question was like this: the disk rotates about z-axis at a constant rate such that the angular velocity of the bar with respect to the ground frame of reference is 0.5 radian per second, and the disk is spinning with an angular velocity of omega s with respect to the bar, okay. So an observer on the bar says that the disk is spinning, while as the observer on the ground says that the bar is rotating. That's okay. Now we know we have to find the velocity and acceleration of point A with respect to the ground. We know from the addition property of this angular velocity that angular velocity of the disk with respect to the ground frame of reference is equal to the angular velocity of the disk with respect to the bar frame of reference plus angular velocity of the bar with respect to the ground frame of reference. This is how it works. This is from the addition property of the angular velocity. Okay, that's equal. We can write this as, this is angular velocity of the disk with respect to the ground frame of reference is equal to angular velocity of the disk with respect to the bar frame of reference, that is omega s vector, and we have plus angular velocity of the bar with respect to the ground, that is 0.5 k cap. We'll write this as 0.5 k cap, okay, which can further be written as, let me, this omega s, now this omega s can be resolved. Let's suppose this angle is theta, okay, let's take this angle to be theta. Now if you look at this right angular triangle, this is 90 degree, fine, this is the hypotenuse, this is base, then we can write in this right angle triangle the value of sine theta. The value of sine theta is equal perpendicular, that's 150 divided by hypotenuse, that is 300, that's equal to 1 by 2. And when sine theta is 1 by 2.5, that means theta is equal to 30 degree. Okay, so our theta is equal to 30 degree. We can cross check it, that sine of 30 is equal to 0.5. That's okay. Therefore we can write this as omega s vector, therefore can be resolved into two components. It does have a component in this direction, okay, and it does have a component in this direction. This angle and this angle are alternate angles. This will also be theta, that is 30, and the component in this direction will be ws cos 30, okay, but along negative y-axis. Okay, so we'll write this as minus ws cos 30, cos of 30 degree along negative y-axis, that is j cap, okay, negative j cap. This component of ws does have two components. One component, let me draw it cleanly. Its component along z-axis, its component along y-axis will be like this, and it does have a component along z-axis that will be like this, right? So we can call this component as, this component will be ws. This is also 30 degree angle, okay, being the course alternate angles, and this will be this along negative y-axis, that's why this is minus, and this component is along negative z, that's why we'll take this as minus ws sine of 30 j cap, oh sorry, sine of 30 k cap, okay, but minus because it's along negative z-axis, and we are having our own plus 0.5 k cap, so this is 0.5 k cap, fine. We can write this as angular velocity of the disk with respect to the ground frame of reference is equal to, this is, we can write this as minus ws cos theta minus ws cos of theta j cap, then we'll write minus ws sine 30 ws sine of 30 plus 0.5, and this is k cap, fine, that's it. Now we don't know angular velocity of disk with respect to the ground, and we in fact do not know this omega s. We are not given the angular velocity, the spinning velocity of this disk with respect to the bar frame of reference. So what we can do, we have, let's take 2 points over here. Let me clean this figure for some time. Let me take 2 points, that is, let's call this as point O, okay, and let's call this point as the point of contact here, point B, okay. Let me write the velocity of point B with respect to the velocity of point O on the ground, okay. We can write, this is something important, velocity of point B with respect to the ground frame of reference, B is the point, by the way, on the disk, is equal velocity of O with respect to ground, velocity of O with respect to ground of frame of reference, plus, okay, angular velocity of the disk with respect to the ground frame of reference, that is omega d j with the ground frame of reference, and cross product with the vector drawn from O to B, okay, that is having magnitude of 300 mm, and it's along y cap. So I will write this as ROB vector in simple terms. Now look at the point B. Okay, the point B is the point which is in contact with the which is in contact with the with is a common point between the disk and the surface, and we are given that the disk is rotating without slipping. Without slipping means we know from the concepts of rotation without slipping, okay, that whenever a body rotates without slipping, the point of contact is the point which becomes a point where instantaneous velocity is equal to zero. If this is point A, its velocity comes to an instantaneous rest. We know this from rolling. Okay, so the point of contact instantaneously comes to rest, though it has acceleration in the upward direction, as we have done in the kinematic analysis. It does have acceleration, but this is the point which instantaneously comes to rest, what we have been calling as instantaneous point of zero velocity. Okay, this point comes to rest. So it means, as far as this point B is concerned, if this disk happens to be rotating without rolling, this point B is the point where we have instantaneous rest. That is, this velocity of point B has to be equal to zero. Okay, this point O does not have a translational velocity at all. It is always at the origin. Therefore, this point is also equal to zero. Now it means that this term is equal to zero, because on the left hand side we have zero. Therefore, what we can get, this is the left hand side is zero. As the left hand side is zero, this term is zero. It means that it means it means the cross product between these two vectors is zero. Okay, but look at these two vectors. The ROB vector is not equal to zero. This ROB vector is not equal to zero. Why? Because ROB vector does have the magnitude equal to 300 mm along y-axis. It's not equal to zero. And angular velocity of the disk with respect to ground is also not equal to zero, because this disk is rotating. Okay, there's no point that this disk is not rotating. It's in fact the spin of this disk which is giving it the angular velocity about the z-axis. That is, this term is not also equal to zero. Okay, when you have the cross product between two vectors equal to zero, with none of the vectors being the zero vector, it simply indicates that the angle between omega vector and ROB vector has to be equal to zero or 180 degree. That is, we mean to say that it gives us the clear indication that the angular velocity of the disk with respect to the ground is parallel to the radius vector drawn from O to B. Why? Because we know if two vectors are parallel to each other, then A cross B is equal to AB sine of theta, the smallest angle between them. When two vectors are parallel, then the value of theta is equal to zero, cross product is zero, or in fact, the value of theta is equal to 180 degree. Still then the cross product between the two vectors is zero. Okay, so it means the angular velocity of the disk with respect to the ground is in such a direction, it is either in the same direction as that of the radius vector from O to B, or it is in a direction opposite to that of ROB. But we know, since the disk is rotating, the sense of rotation of this disk is clockwise. If we curl our fingers in this direction, okay, the sense of rotation has to be in the opposite direction. Okay, it has to be in this direction. That is, the angular velocity vector has to be in this direction. It has to be along y direction, but essentially it has to be in the negative y direction. Okay, because our sense of rotation of this disk, sense of spinning of this disk is clockwise. Okay, if we, it's clockwise curl, it's clockwise rotation. Okay, so its angular velocity vector will be along y direction but in the negative y direction. This is what the cross product states to us. Okay, so it means we can therefore write this as, we can hence write here that angular velocity of disk with respect to ground, its magnitude is, say for example, omega, but it will be along negative y-axis. It's along negative y-axis. Okay, angular velocity of the disk with respect to ground has magnitude omega, but it's negative, it's along this direction. Okay, if this disk would have been spinning in this direction, in the anti-clockwise, then certainly this would have been along y-axis like this. Okay, in the direction of the thumb. The thumb gives us the indication of its sense of rotation. Okay, anyways, so we can write this as, this is minus ws cos of 30 j cap minus ws sine of 30 plus 0.5 k cap. Now balance the vectors. Okay, so we'll write, we have ws sine 30 plus 0.5. We do not have a component, therefore this term is equal to 0. Okay, let me rub it over here so we can write it over here. Can we can write this as, let me put it somewhere here, separate this. Therefore we can write this as, we will have minus ws sine of 30 minus ws sine 30 plus 0.5 plus 0.5 is equal to 0. Therefore from here we'll get omega x 0.5 divided by sine 30. Sine 30 is also equal to 0.5. Therefore omega s, that is angular velocity of the disk with respect to the bar frame of reference, is equal to 1 radian per second. This is omega d. Now this is omega s. Okay, substitute omega s here, we'll get minus omega, or what we also have written as angular velocity of the disk with respect to the ground is minus ws, that's minus 1 cos of 30. Okay, so omega comes out equal, cos of 30 is equal 0.0, so omega s is coming out equal to 1, and we'll have this as equal, cos 30 is equal, this is minus cos 30 is 0.866, so this is 0.866 radian per second. This is done. So we could find the two values. Okay, we could find the two values. We have found the value of omega s, that's angular velocity of the disk with respect to the bar. Its magnitude is 1 radian per second. And omega, that is angular velocity of the disk with respect to the ground. Okay, angular velocity of the disk with respect to the ground is how much? It is, I will write here, angular velocity of the disk with respect to the ground vector, it's equal minus 0.866, it's equal to 0.866, 0.866, okay, minus, but it's along k cap. Okay, so I will write here, it's along, sorry, j cap, that's here, omega j cap minus omega j cap, that's minus 0.866 j cap. This is the angular velocity of the disk with respect to the ground. Okay, fine, we are done with this. Now let's find the angular acceleration. Again, using the same expressions as we have already discussed while discussing the kinematics of rigid bodies. We'll write it as, okay, what we can do, let me rub this as well, this as well. Okay, I can write now. Let's talk about the angular acceleration of A. Okay, so as far as the angular acceleration of this disk is concerned, the angular acceleration of a disk, we know we represent by alpha. In fact, we represent as alpha vector. Okay, so angular acceleration of a disk with respect to, we have to find the angular acceleration of the disk with respect to the ground, because we have to use formula for velocity and acceleration, which definitely involve the term of angular acceleration. So once we talk about the angular acceleration of the disk with respect to the ground, that's equal to the derivative of, that's equal to the derivative of the angular velocity of the disk with respect to ground and its derivative with respect to the ground frame of reference. We have to define the angular velocity of the disk with respect to the ground, and we have to take its derivative with respect to the ground frame of reference. That will give us the angular acceleration of the disk with respect to the ground frame of reference. Using the property of the theorem of the product of a vector in two different frames of reference, we are having two frames of reference, the ground frame of reference and the what we call as the bar frame of reference. Therefore, we can write this as angular velocity of the disk with respect to the ground frame of reference. Its derivative we have to take in the ground frame of reference is equal to angular velocity of the disk with respect to the ground and its derivative with respect to the bar frame of reference, to a bar frame of reference, plus angular velocity of the bar with respect to the ground frame of reference, angular velocity of the bar with respect to the ground frame of reference, and its cross product with the angular velocity of the disk with respect to the ground. Angular velocity of the disk, because we are taking the derivative of angular velocity of the disk with respect to the ground, our vector is angular velocity of the disk with respect to the ground. Its derivative like this. Fine. We know as far as angular velocity of disk with respect to ground is concerned, angular velocity of the disk with respect to ground is 0.866 j cap. Okay, and once we take its derivative, it's constant, its derivative will be equal to 0. That's this term is equal to 0. Therefore, the derivative of angular velocity of disk with respect to ground, its derivative with respect to ground frame of reference, that is angular acceleration of the disk with respect to ground, is equal to angular velocity of the bar with respect to the ground, that is 0.5 k cap, 0.5 k cap, and cross product with angular velocity of disk with respect to ground, that is minus 0.866 j cap. Okay, so once you calculate it, it comes k cross j. K cross j is equal to minus I, minus minus will become plus. It becomes equal 0.4330 I cap, and the units will be radian per second square. This is angular acceleration of the disk with respect to the ground frame of reference. Okay. Now we have to calculate, the question says calculate the velocity and acceleration of point A. So let's calculate the velocity. So it's a very simple steps now we can perform. Okay, let me write here the expression. We know velocity of point A. In order to find the velocity of point A, what we have been doing, we draw a vector from point this to point A. Sorry, undo. We'll draw the vector from this point to this very point. Fine. And as far as this vector is concerned, this will be having the what we call as its, this is one of its, this is its z coordinate, and this presents its y coordinate. Fine. So what we can do now very quickly, now as far as this distance is concerned, the distance from here to here, let me also draw it cleanly, the distance from here to here. Okay, sorry, can draw it from here to here. Let me write this as point O, and let me call this as point C. Okay, I had earlier called this as point B, no problem. Now in this right angle triangle, this angle is equal to 30 degree. Fine, this is 30. Now this is a right angle triangle. Okay, this is its hypotenuse is 300 mm, and its base happens to be 150 mm, that is 0.15 meter, and this is 0.3 meter. Fine. So we are having a right angle triangle with hypotenuse equal 0.3 mm, with perpendicular equal 0.15 mm, and as far as the base is concerned, the base happens to be this happens to be 0.33 mm. Let me further calculate it. 0.3 raised to power 2 plus 0.15 raised to power 2, 4 raised to power 0.5. It's equal to 0.33. This dimension is coming, the base is coming out to be 0.33 mm. Oh, sorry, 0.33 meter. Fine, 0.33 meter. Okay. Now, as far as this dimension is concerned, okay, from here to here, from here to here, this will be, from here to here it will be 0.33 cos of 30 from here to here. Okay, from here to here it will be 0.33 cos of 30. Okay, so if we are subtracting uh, 0.3 minus 0.3 cos of 0.3 minus um, 0.3 cos of um, 30, so certainly we will get it, get this to be equal to, okay, or we can do it like this. We can, let's not find this one, let's draw the perpendicular from here to here. We can draw the perpendicular from here to here. Okay, okay, even if you okay, fine, if we still draw the, that is this point, we have to find how much is this distance. Let me remove the previous one. Now as far as this distance is concerned, this distance should be, yes, the easiest procedure of doing it or finding it can be done like this. Let me rub all these lines. We do have, let's complete this line. Okay, from A to B, this is the diameter, this will be 300 mm. From here to here, draw a line like this. Okay, and therefore we can simply write, this total distance is 0.3 meter. This angle is 60 degree because this angle is 30 and this angle is 90. Fine, this angle is 30 degree, this angle is 90, this angle will be 60. Fine, this distance from here to here will be equal 0.3 cos of 60. Therefore this coordinate along y-axis, the coordinate of OA along y-axis is this coordinate, and this coordinate will be this total distance, that is 0.3 minus 0.3 cos 60. 0.3 minus 0.3 cos 60, and the coordinate along y-axis will be 0.3 sine 60. Fine, so we can write this as far as the radius vector from O to A is concerned, ROA vector is equal, it's equal 0.3 minus 0.3 cos 60, cos of 60 j cap. Okay, let me again clean this along j cap plus 0.3 sine 60, sine of 60 k cap. Fine, we'll close it. This is ROA, and if we solve it, then ROA vector comes out equal, it becomes 0.5 j cap plus 0.2598 j cap, 0.2598 k cap. It's like this. This is the radius vector from O to A. We write this as ROA vector. This is how we write it. Now write down the expressions. Remember all these. Remember all these expressions. Okay. Let me clean all these things from here so that I can write the final components, final equations for velocity and acceleration. I will write velocity of A with respect to ground is equal to velocity of O with respect to ground plus angular velocity of A with respect to ground, and the cross product with the radius vector drawn from O to A, that is R OA vector. Fine. Now velocity of O with respect to ground is equal to 0 because this point always is at rest. Okay, O is always at rest. Therefore the expression becomes angular velocity of A with respect to ground, that is minus 0.866 j cap, 0.866 j cap cross product with ROA cap, that is ROA cap is 0.5 j cap plus 0.25 98 k cap. Like this. Okay, so once we perform this cross product, we'll get velocity of A with respect to ground is equal to, comes out equal, j cross j is 0. Okay, fine. So we have 0.866 multiplied by 0.2598. It becomes equal to minus, because j cross k is I, but you have your minus, so it will be minus 0 0.225 I cap meter per second. Therefore, this is the first expression that we have calculated. Let me clean these expressions here. That is, we have got velocity of A with respect to ground is equal to 0.225 meter per second along I cap, but negative. This is fine. This is the first expression that we have obtained. Now let's write down the acceleration expression. So we know acceleration of A, this is the last line we have to write. Acceleration of A with respect to ground is equal to acceleration of O with respect to ground plus angular acceleration of the disk with respect to ground, cross product with the radius vector drawn from O to A, ROA vector, plus angular velocity of the disk with respect to ground, multiplication with the angular velocity of the disk with respect to ground, dot product with ROA vector. This expression we are familiar with, ROA vector, fine, minus ROA vector in multiplication with angular velocity of the disk with respect to ground, dot product with angular velocity of the disk with respect to the ground. That's it. This expression. Linear acceleration of O with respect to ground. O happens to be at rest, therefore this term is equal to 0. Rest of the terms we do know. We know angular acceleration is equal to, alpha comes out equal, the value of alpha is 0.433 I cap cross ROA vector, that is 0.5 J cap plus 0.259898 K cap plus angular velocity of the disk with respect to ground, that is minus 0.866 yeah, 0.866 J cap multiplication with this term, okay, that is 0.866 J cap dot product with ROA, that is 0.5 J cap plus 0.2598 K cap, 0.2598 K cap. Fine. We are done with this. Let's close this bracket. This is dot product. Okay, fine. Then we have minus ROA vector. Let me write these terms here. Okay, so ROA vector is 0.5 J cap and it's dot product with angular velocity of the disk with respect to ground dot angular velocity, that is minus 0.866 J cap dot product with 0. But minus 0.866 J cap. This is quite an easy expression to calculate, which I am leaving as an homework to the students. First take the cross product, then take the dot product, multiply with this term, take the dot product, multiply with this term to obtain the to obtain the expression for the acceleration. And once we do it, let me check it. The value of acceleration of A with respect to the ground will come out to be equal, please perform these steps, it will come out equal minus 0.1125 j cap minus 0.130 k cap. Since our r is in meters, therefore it will be, acceleration will be meter per second square. So we have calculated acceleration of A, and we have also calculated the velocity of point A. Hence, the question stands solved. Thank you very much.